So far, whatever problems on fluid mechanics that we have solved, all of them, in all of those problems, the fluids were non-viscous. So there was no frictional viscous force applicable in those problems. Beginning this video or beginning this problem, we would be starting to solve cases where we have viscous fluids. Now, under viscous fluids, we have basically three formulas for viscous flow problems. We would be keeping ourselves confined to those three problems, usage of those three problems in solving viscous motion problems. Okay. So what were those? The number one was the basic viscous force equation, which was given something like this. Okay, if you remember. The second was the Poiseuille's equation, and the third was the Stokes' law. So you would be solving a few problems on these three equations. Okay. Let me give you the first problem. The first problem is on equation number 1. See, equation number 1, where we define viscous force is equal to eta times cross-sectional area times dV dz. Okay, this is nothing but a differential equation. Differential equation is something which you would be studying in detail in your mathematics courses. But let me tell you that when you are solving differential equation, in order to get a neat solution on this, you need something called boundary condition. Okay, I would explain briefly what is a boundary condition, but again, this is a terminology used in the mathematics courses. I would not get deeper into it. Let me first define the problem. The first problem that we have for you, it's basically a warm-up problem on viscous flow. Let's say there is a fluid, okay, which is kept somewhere. Okay, let's say this is a long container and the fluid is kept. Okay, now what is done is flat, okay, a flat board, you can say, of certain cross-sectional area. Let's say cross-sectional area equals to A. It is moved on the surface of this fluid. Now, the depth of the fluid within the container, this height basically, is equal to H. The density of this fluid is, let's say, rho. This fluid is viscous. The viscosity of the fluid is, let's say, equal to eta. Remember that this length of the container is much longer as compared to its height and the size of this board that I am moving. Okay. Now this board is moved on the surface of the fluid with a velocity of, let's say, v0. What you have to do is you have to find out the velocity gradient, or you have to find out the velocity of the fluid and how it varies along the depth. Okay, so let's say at a depth of y, you have to find out what is the velocity of the fluid. Remember, the board is moved with a velocity of v0. The fluid has a depth of h, and this length is much larger as compared to other dimensions. The fluid is viscous. The coefficient of viscosity is eta, and the density of the fluid is rho. You have to find out the velocity gradient and how the velocity within the fluid varies with depth. You would also need to find out what is the viscous force acting, okay, within the fluid. It's a very, very simple problem. It's just an application of this equation. Try this out. If you are not able to solve it, we would be solving this problem in the follow-up video. Thank you.